some stuff.
Right, I think we're going to take a quiz next Tuesday. Let me just get that on camera here. Quiz Tuesday, what day is that? The 18th? October 18th. On whatever, you know, probably parabolas, probably vertex and x-intercepts and all that. What I hadn't done so far in the first couple days is I hadn't really got to any good word problems. There's some in the homework. I'll probably look at some more next week, but let's start with a classic word problem, and that is, that's this. So I'm still kind of in 3-1 or 3-2 looking at this word problem. So I'm going to write a couple sentences here because it's a word problem. I am standing on top of the library. The library is about 74 feet above the ground. I throw my calculator, because I can just do math in my head, you know, I don't need a damn calculator. So I throw my calculator up in the air with an initial velocity. So I have to, you know, when I throw it, I can throw it weakly or strongly, or the other thing I could do is just let it go. I could do a lot, there's a lot of things. I could throw it down, I could throw it up, I could just let it go. But all that is sort of about the initial velocity with which I throw it. So I'm going to say I threw it up with an initial velocity of I'm going to say 52 feet per second. So that's the word problem. Now, maybe in some more advanced classes, maybe I'd make you memorize the formula that this all goes in, but I think I'll just tell you the formula this goes in. After telling you that word problem, then here's the function for the height of this flying object here. The function is, I'll use h of t. It is going to be a function of time, and here it is. It's negative 16 t squared. And then the initial velocity goes right here times t, so that's 52t. That's that initial velocity. And then that initial height goes next. That's 74. So, I mean, I'm telling you where these numbers go. I'm telling you why, but the truth is you don't have to memorize where these numbers go. I think I'll describe a word problem and give you the formula. I could make you memorize where these numbers go and develop the formula yourself, but I don't think I will. I'll just give you, this is the formula for the height of this object. As a function of time since you threw it. You know, the picture looks like this. I mean, this is a real physical problem. So it starts at t equals 0. I mean, and we discussed y-intercepts, we discussed a lot of cool stuff, but just let's think about the reality of this problem. At t equals 0, where are you? I mean, you could read the problem and tell me, or you could use the equation and tell me. But because at t equals 0, you plug in a 0 and you are at 74. There, you're at the top of the library, 74 feet up. And I say you, but I'm really talking about the object I'm throwing, I guess. The calculator is at t equals 0, it's on top of the library, 74 feet. So watch this. At t equals 0, it's at 74 feet. This x-axis is the t-axis. It's t instead of x. And this y is height. It's a function of t, so my y-axis is height. Okay, so as time goes on, what happened? I mean, what happened 1 second later? What happened 2 seconds later? What happened 3 seconds later? As time clicks on, what's this thing doing? And I could plug numbers in and plot points, but I don't really want to plot a bunch of points. What is happening? I threw it up, right? So what's it? 1 second later, it's probably a little higher than it was. You know, even though I threw it at this speed, immediately as soon as it leaves my hand, this speed starts changing. Gravity slows it down. As soon as it, a half a second after it left my hand, it's less of a speed. And in fact, so it's kind of slowing down. Gravity wants to pull it back to Earth. But anyway, maybe after the next second, it still goes a little higher. At some point, though, it does reach a maximum height. It actually stops at that second. It stops at that brief second. I mean, you can't see it. Watch, can you see this stop? Maybe you did. Okay, it's brief. It stops and turns around and starts heading back toward Earth. 3 seconds later, maybe it's here. 4 seconds later, maybe it's here. It speeds up as it heads to Earth. Gravity accelerates it toward Earth. At some point, it hits the ground, I guess. And the shape is a parabola, of course, but it's the height as a function of time. I want to say something. What I did not do, I really didn't stand on top of the library and I didn't launch this thing out over the grass. So it's not, the path of the calculator is not really a parabola. I threw it straight up. And I might not have said that exactly, but I threw it straight up. I went straight up and it comes straight down right next to me. So the path doesn't really look like a parabola. But when you graph it as a function of time, how long it's been in the air and how high is it, the shape is a parabola. That first second it went pretty far. The second second it went less far. The third second it was on its way down. The fourth second it was really speeding up. So I'm just saying, it's the picture of a video of the calculator is just straight up and straight down. As a function of time, it's a parabola. It's this equation. It's an upside down parabola with a y-intercept at 74, you know? I mean, there it is. So, that's a long description. What's my question? My question is, there's a few questions. When does it reach maximum height? Let me spit out these questions before I answer them. And part B, what is the maximum height? What is the maximum height? Part C, when does it hit the ground? When does it hit the ground? Part D, there is a sweet little bluebird flying. Well, bluebirds don't fly that high. Listen, and they're sweet. You know, how about there is a vulture, a turkey vulture, flying around at a height of 105 feet. When do I hit the bird? So these are all pretty cool questions. And I think you guys are smart algebra students. I think you can handle this. It is a word problem setting, but we've been practicing parabolas, and all this really is all the parabola practice we've been doing just set into a word problem. I don't know, let me help you. I already previewed this the last few days. When someone asks for maximum height, what are they asking for?
The vertex.
Thank you, the vertex. So this little pictures might help you. Yeah, I need the vertex. But notice something, you know this, the vertex always had two parts. It had an x value and a y value. Well, that's sort of what goes here, my two parts. Can you tell which one goes where? The first one wants to know when. When they use the word when, I think that means time. And time is my x. So I think this first question is the x value of the vertex. Is that logical? Okay, that's logical. It's the x value, or in this case, t value. And then I think, what is the height? I think the height is the y value of the vertex. So these questions are about the vertex, but more specifically, I think you can read these words and understand what I just told you. That's the x value, and that's the y value of the vertex. By the way, they could be asked in a different order, but even if they're asked in a different order, don't you do this one first? I mean, you need the x value before you can get the y value of the vertex. So here I go. I memorized my formulas. I know this is easy. Let's do this. That's negative b over 2a is what it is. It's the x value. Again, I'm calling it t here. But here we go, negative b over 2 times a. So negative b over 2 times a, that's negative b over 2, yeah. So that's 52 over 32. I don't know how nasty that is. Somebody...
1.625.
Okay, 1.625, thank you. I do want a decimal. This is a word problem where I think decimals are appropriate. I also suggest we don't round it too much. I mean, I would round it to 1 or 2 decimal places, but since this one came out exact, I think I'll just keep that 3rd decimal place to keep it as exact as I can. If it was a nasty long decimal, I might round it to 1 or 2 decimal places, 2 decimals. But I'm going to just leave it like that. That's a good answer. That's the exact time. I don't want to round it. That's when it's maximum height. Cool. How do I find the y value?
Plug that number back into t.
Plug that number into the function. That's what we've learned that the last few days. So h of 1.625 is the y value. This is, it's negative 16. It's 1.625 squared. You need a calculator. You probably ought to practice doing this and see if you can get this answer. You got to square this, then you multiply by the negative 16. You kind of got to know your order of operations. You multiply this. Then this is negative here, so then you'll add these numbers. Anybody have an answer for me?
116.25.
Okay, cool. And that's feet. That was seconds. That was the time it took to get to maximum height. This was the actual maximum height. And if I go back to my picture, it's not the best picture, you know, I roughly drew it. At 1.625 is where we should achieve maximum height. I think I'll just adjust my picture here a little bit. You guys okay with that? And what is that maximum height? 116.25. Cool. Cool. That's pretty cool. It's easy. It's just a vertex, but it's set in a word problem. You know, students are funny. You guys are not. Some students are funny. They make this is hard. I mean, this is hard for students. I think it's just the words scare students, but it's just the vertex is all it is. And guess what this is? When does it hit the ground? When does it hit the ground? I'm looking for the time it takes to hit the ground. I'm looking for this time right here when it hits the ground. Basically, you could interpret that as
0. T-intercept.
Yeah, I was going to say the x-intercept, but the appropriate language here is t-intercept, and that's something about 0. What's going on with the t is not 0, but the height is 0, of course, when you hit the ground. So what are you doing? When you hit the ground, the height is 0, and you have got to solve a little quadratic formula. Well, you got to solve a quadratic equation. Sorry, you got to solve a quadratic equation. We practiced this last class. Factoring, with these numbers, these big nasty numbers, I would just jump on the quadratic formula. And I would let my calculator help me do it. You know, we kind of practiced the quadratic formula a little bit the other day. And I kind of I didn't jump on my calculator too quick. I wanted to keep the answer pure and exact. In this word problem, I don't mind a decimal version. You'll see what I mean. Let's do it. The quadratic formula, t is negative b plus or minus the square root b squared, wow, that's 52 squared, minus 4 times a is a negative 16, and c is a 74. So these are some big numbers, and we're going to get a big number in the square root there, all over 2 times a. 2 times a would be a negative 32. But now I'm going to work on this square root like I previewed the other day. That's 52 squared. It's going to be plus. Do you guys see that? It's going to be plus whatever that big number is. And I'm going to avoid writing too much. What I'm going to do is I'm going to do 52 squared plus 4 times 16 times 74. and I'm getting 7440. So let me just, I'm going to do a little sloppy work here. That square root is 7440. And now what is the square root of 7440? Like I said, I don't want to simplify it exactly like I want to use my calculator and make it a decimal. What is the square root of 7440? 86.26. This is where I'll round this. 86.26. You guys okay? So now where am I? Okay, that was the square root, cleaning up the square root. We did a good job. So where am I? I got negative 52 plus or minus 86.26 all over negative 32. So I should do both these little problems. I should do negative 52 plus 86.26. Let me see what that is. And then divide that by negative 32. Watch out, don't lose that negative. A lot of students lose their little negative 32. It is negative 32. So I just did the plus version here, and I got negative 1.07 seconds. Let's do the minus version. If I subtract that, negative 52 minus the 86.26, do it slow and careful, and then divide by the negative 32. Now I'm getting a 4.32. I mean, we did expect two answers, right? The quadratic formula gives me two answers. If I go look at the picture, it looks like I should have one answer. Well, that's because the other leg of the parabola is over here. The other leg of the parabola comes down like this. And so here's my two x-intercepts. But for the reality of this problem, I don't want this one. This doesn't even exist in the reality of this problem. This is kind of ain't here, right? I mean, the problem started when you threw it from the top of the building, so the problem started here. But I'm explaining why is there two answers. The math says there's two answers, but in the reality of this problem, we toss this one out. So we do the work, but we toss this one out, and I kind of like to see you do that. You know, that shows me what you're doing and what you're thinking, and so there's the answer. Cool. That's pretty cool. When does it hit the ground? 4.32 seconds. Again, my picture's just a little off here. Not too bad, though. If that's 4, it should have been over here a little more. A little steeper right there. Cool. With a whiteboard, you can adjust accordingly. That's awesome. That's been rounded off. That's okay. I mean, the 86.26 was rounded off. This answer is just a little rounded off, but that's good enough. That's what we expect. Cool. One answer. When does it hit the ground? One time. That time, 4.32 seconds. And it's just a quadratic formula. It's kind of a nasty quadratic formula, but you get to pick up your calculator and use it, you know, so that helps. All right, what about this one? There's a vulture flying at 105 feet. You know, when I wrote that problem, I was sort of thinking of putting it at, the vulture is flying at 125 feet. That's what I think I was going to put that for a minute. If I asked you that question, the vulture is flying from 125 feet. Let's say it was 125 feet. There's a vulture flying up there. When do you hit the vulture?
Never.
Never. It doesn't hit the vulture, right? And that's, you don't have to hardly show any work. If you knew what the vertex was, if you knew what the maximum height was, you could sort of, right, say never. If you did the math, I think what you get is imaginary answers, which would indicate never. Okay, but that's if you're at 125 feet. Hold on, we're going to get answers. We're going to get answers because ours is at 105 feet. Our vulture is flying around here. I mean, I really got nothing against vultures. They kind of, I wouldn't want to cuddle up with one, but they serve their purpose. Yeah, he's flying around out here. I think I will hit him. In fact, I might hit him twice. I think on the way up I could hit him, and then on the way down I could hit him again. So what do I do? When the question said, when does it hit the ground, we set it equal to 0 because the ground has a y value of 0. When the question says, when do you hit the vulture, we set it equal to 105 because the vulture has a y value of 105. So I want to know, when does the y value equal 105? So now I'm solving this quadratic equation. Now, just last class, we started practicing solving quadratic equations, and one of the the first steps is, do you know the first step? You need it equal to 0. You need it equal to 0. So the problem starts by setting it equal to 105 because that's the logic of the problem. But then when you start doing the math, the way you solve a quadratic equation is you need it equal to 0. So I'll move the 105 over here. I'm subtracting 105. It turns into this problem. 0 equals negative 16t squared plus 52t minus 31. So this is the new quadratic equation I need to solve. I'm running out of room just a bit, so I think I'm just going to erase this and move up here. Solve this quadratic equation. On your mark, get set, go. Quadratic Formula champion from 1985. Let's see, here we go. Shit, I'm bogging down here. Negative b, yeah. Negative b plus or minus the square root b squared minus 4 times a times c. Okay. All over 2a. 2a would be a negative 32 again. All right, I'm going to work on that square root. You know, this time I'm minusing, that'll be a positive number, won't it? Those two negatives will make it positive. I'm subtracting a positive number. Or you could say there's 3 negatives there. That's going to be negative, so I'm going to be subtracting. Anyway, got to get that right somehow. Here it is. It's 52 squared minus 4 times 16 over 31 is how I'm doing. Cool, 720. That's the square root of 720. What is the square root of 720? 26.83. 26.83. So this problem just turned into negative 52 plus or minus 26.83 all over negative 32. Right? I should have left myself just a little more room. I'm moving over here. Negative 52 plus or minus 26.83 all over negative 32. Now you try to execute both of these. You do the plus, you do the minus, and get this answer. Negative 52. Negative 52 plus 26.83. That's a negative number, but when you divide by negative 32, it becomes a positive 0.79 seconds. So that's one time you can hit the vulture. And I think there's another time. Let's see, it's the negative 52 minus the 26.83. And then divide that by negative 32. I always hit enter. I do my numerator, hit enter, and then I divide by negative 32. 2.46 seconds. And then this time, there really is 2 answers. We don't toss one of these away. There is 2 chances to hit the vulture. Yeah. This is good stuff. Like I said, I mean, there's some work. You got to get organized. You got to be willing to do the work, do the quadratic formula. You got to memorize it, and you got to do it. Yeah, it's pretty good stuff. Like I said, a step up from chapter 1 or 2. I think you should practice for this quiz and test and stuff next week. Any questions? There's other word problems in the homework about, profits and costs and minimums and maximums. There's even an equilibrium thing, I think, where you set the supply equal to the demand again, but this time it's quadratic. We did that in chapter 1. It was linear. But but supply and demand equations where you set them equal to each other and try to solve. There's some good stuff. I think I'll help you more with some of that next week, but it's usually just solving quadratic equations and finding vertexes. That's what this is. Until we move to 3-3. Let's do that today. Let's move into 3-3. And 3-3's got a few different ideas going on here. So we're kind of leaving parabolas in a way and working on some different ideas here in 3-3. So hang in there. I guess I'm going to present it like this. Some books are a little different, but I'm going to call this a library of functions. So I'm kind of leaving parabolas for a second, and I'm exploring several different types of functions here. Now, and I want to kind of explore their real basic versions. Now, look at this guy. I mean, this shouldn't even count, to tell you the truth. I don't think you'll see this in chapter 3. I mean, I'm putting him up here, but what is he? He's a function, and what is he? Tell me anything about him. Can you say he's a line? That's what I wanted to hear. He's a line. He's a line. He's a line. He's he's a kind of such an easy line. He throws people off sometimes. This is a line. He's got a slope of 1. He's got a y-intercept of 0. I mean, it's such an easy little line. It kind of throws you off. It goes through 0 and it goes up 1 over 1, up 1 over 1, and it's just this line. I don't know. I just thought I'd remind you of that. Let's move on. But we should know that basic line. Okay, look at this guy. Here's y equals x squared. We talked all about quadratic functions and parabolas, and I did all these different parabolas in different places. But I never did this real basic dude. I'm sorry. Maybe I should have opened with this real basic guy. This is the most basic parabola you can have. The most basic quadratic function you can have. His vertex is 0, 0, and he just opens up, and so he's just this kind of standard parabola. I would just call him your most basic standard parabola. I mean, when you start adding a 6x plus 7, then you start moving it around. The vertex gets moved, and it's different. This is just your most basic standard parabola. By the way, hang on one second. When you plug in a 1, plug in a 1 for x, what's y?
1.
Thank you. So this goes through the point 1, 1. So does this, by the way. When you plug in an x is 1, y is 1. But it has a different curve to it. It's got this curve to it. Check this out. Here comes his cousin. His cousin. I call him his cousin. It's the square root of x. Why is it his cousin? Well, this is x squared, and then this is the square root of x. They're kind of related. The word is they're inverses of each other. That topic comes up in chapter 4. But they are inverses of each other. One of them undoes the other one. One of them squares x's, the other one square roots x's. So they're kind of related. I'll get to, chapter 4's got some more stuff about that. Well, anyway, watch this. Here's what he looks like. He's a square root function. Oh, you know what he is? He's that sideways parabola, but he's only the top half. He's the top half of a sideways parabola. And by the way, when you plug in a 1 for x, what do you get for y when you plug in a 1? Plug in a 1, what do you get?
1.
Thank you. See, I don't know, these are cool. These are all going through the point 1, 1, but notice the curve, and the book refers to that as concavity. See how this guy's curving? They call that concave up. See how this one's curving? They call it concave down. It's not that hard, but it's the concavity. It's the way it's curving. By the way, they're both going through 1, 1. He's getting bigger and bigger and bigger. This guy's getting bigger too, but at a way lesser rate. This function grows. The y values grow very huge, very quick. This function, the y values grow pretty slow. Takes a while. I mean, if you plug 100 into this function, if you plug 100 in there, the answer is 100 squared. I think that's 10,000. Watch this. If you plug 100 in here, what do you get? 10. So on my graph, if I went way out to 100, how high would I be? 10. See, so it's a, I don't know, it's a totally slow-growing function. All right, let's keep talking. Here's this guy. I'm going to put him over here. Y equals x cubed. By the way, I'm putting these equations on the board and then I'm drawing you these pictures. Is that a mystery? I mean, how does this equation become this picture? I mean, I'm just, and by the way, when x is 1, what's y? 1. It goes through that point 1, 1 again. This time it goes a little, I don't know, it's still concave up over there. It's a little lower though. It's kind of lower there, and then once you get past 1, it gets steeper, man. It gets really steep. It's really steep because it's cubed instead of squared. It's steeper than this guy. Well, it's steeper for this guy after 1. Before 1, he's kind of shallower than this guy. It's kind of funny. All right, his cousin. His cousin is the cube root of x. This is x cubed, and it looks like this. It has this snake shape like this. The cube root is the cube root of x. Looks like this. Again, it's the sideways version of this. Remember I told you this was the sideways version of this, except it was just the top half. This is the sideways version of this. If you flip him sideways, and you got to flip him over a little bit, it's this. And by the way, it goes through the point 1, 1. My picture's getting a little off there, but it is. Looks a little better. It's got this sideways S curve thing. The cube root of x. It's got this different concavity. I think I got a couple more for you. And I guess what I'm asking you to do, by the way, is memorize these. I mean, so there's going to be, I think there's a couple more. So there's kind of 1, 2, 3, 4, 5, 6, 7. 6 or 7 of these. You may not want to count that one, but you should know that one. But 6 or 7 of these that you should just memorize their shapes. Their equation and their shape. Their equation and their shape. Basic equation and basic shape. I think next chapter we start shifting these things around. We don't do it, doesn't happen this chapter. So next chapter we can shift this around and we can move them over 12 units, move them up 15 units. I mean, you can, I'll teach you that. Right now I want you to memorize basic shapes before we shift them. Here's something else though. Hang on, I'm getting there. I'm getting there. This, but I need to bring this up. This square root of x. Now this is an old intermediate algebra idea in a way. A square root of x can be written as, see, all these things have an exponent. It's x with an exponent on them. An exponent of 1, an exponent of 2, an exponent of 3. But this is the square root of x, which is an exponent of a half. And I feel like somebody told you that in intermediate algebra, but you might be out of the blue here, so now I'm telling you again. Roots can be written as exponents, but they're fractional exponents. You know, one way to think is to think of that number there as the root, and then that number up there as the power. So this was a square root, and so I wrote the root was 2. So it's x to the 1/2. Look, this is a cube root. A cube root, we put the little index 3 there to indicate it's a cube root. What if it was a 4th root? We put a 4 there. What if it was a 5th root? We put a 5 there. What if it's a square root? If it's a square root, we've agreed we don't need to put a 2 there. We know what it is. You with me? Okay. So if this is a cube root, what's another way to write it? X to the 1/3. That's what he is. It's equivalent. The root is in the denominator. The power is in the numerator. When you have fractional exponents, they are roots. What if you have x to the 5 halves? What the hell is x to the 5 halves? It's a root. What kind of root is it? It's a square root. It's a square root of what? It's a square root of x to the 5th. The 5 is the power that goes on x. We called it the 5 is the power that goes on x. See, this one just had x to the 1st. You guys with me? Mm-hmm. X to the 1st. The root was 2. This one, the root is 2, but it's x to the 5th. By the way, I like this. This is fine. I don't want to clean this up, really. I'm just trying to, the truth is, I want to write it like this, but I want to teach you what that means. But it is the same thing as, watch this, it is the same as the square root of x to the 5th. You can either put the power inside the root, or you can put the power outside the root. Doesn't matter. It's the same thing. Okay, all right, all right. So there's a big idea here. Your book, excuse me, your book refers to this as power functions, kinda. I don't know if I care to use that word, but it's okay. I mean, they all have, we got powers on x. We got all these different powers on the variable x. And I want you to see this pattern. Look at this. So when it's x to the 1st, it goes through this point 1, 1, and it just goes straight through. But anyway, it's a line. But if you start changing that 1, if that power becomes more than 1, like, watch, like 2 and 3, then what happens when the power becomes 2 or 3? Then it starts to bow this way. The curve kind of turns concave up. It still goes through the point 1, 1, but it has this concave up curve. Like these two guys, see them? X squared, x cubed is even steeper. X to the 4th is steeper. X to the 5th is steeper. What if the power is less than 1? Like 1/2, 1/3, 1/5, 2/5, 2/3. If the power is less than 1, it's got this shape. It's coming out of the origin, and it bends this way. Dude. I mean, what am I saying? I'm saying, I've said all that. Now here, watch this. I'm talking about power functions where we have x to a power, and here's a little picture that helps. I'm not really care about the rest of the graph. I'm sort of focused on this first quadrant here. We call this quadrant 1. Did you know that? Quadrant 1, quadrant 2, quadrant 3, quadrant 4. But I'm focused here on, and I'm saying, what am I saying? If they go through this point 1, 1, unless somebody multiplies it by 3 or something. And if it looks like this, that means the power n is 1. If it looks like this, that means the power is less than 1. Is that what I'm saying? And if I go like this, that means the power is greater than 1. I mean, that summarizes everything I just tried to say. And it's called concave up if it holds water, concave down if it spills water. And these are just a category of things that have these shapes, and it's power functions. And these sort of fall into that category. I mean, they do fall into that category. But that's sort of a separate little topic. This is about how do they bend, how do they curve, what's their concavity. This is about, please memorize these shapes. Please, I want you to know these shapes. That's pretty good stuff, man. That's pretty good stuff. Let me show you 2 more functions that don't really fit the power function category. But there's 2 more I'd like you to know. Here's one. I'd like you to know this basic shape, the absolute value of x. This is a function. This is sort of in my list. Maybe I just kind of ran out of room here. So in my list of 5 functions, here comes number 6 here. The absolute value of x. You know, the other day I sort of taught you how to break that down. Let's just, I'm just going to tell you it's this. It's this V-shaped graph. It's this V-shaped graph. The absolute value of x. It's a straight line. These are straight lines. This doesn't curve. These are straight lines, and it's this V-shaped graph. I'd like you to memorize that, I guess. You know, I'm asking you to memorize this stuff like it's magic, you know. If you want to understand any of these shapes, do you know what to do? I mean, my teacher told me that this is this shape. I don't get it. How do you get it? If you want to get it, how do you get it? Do you know what to do? Thank you. That's what you do. If you really want to understand why is this equation this picture, then you make a little chart and you plot points. Exactly. That's what you do. What? Plug in a -3. What's the absolute value of -3? 3. Plug in a -2. What's the absolute value of -2? 2. Plug in a -1, you get a 1. Plug in a 0, you get a 0. Plug in a 1, you get a 1. Plug in a 2, you get a 2. I mean, that's, if you plot those points, that's these 2 lines. When it's -3, it's 3. When it's -2, it's 2. You guys with me? But that's true for any of these guys. You know, this x cubed. Why is it this S-shaped thing? Well, you know, when you plug in a -2 and cube it, it's -2 times -2 times -2, which is -8. So when you plug in a -2, it's way down here at -8. What happens when you plug in a +2? 2 times 2 times 2 is +8. So that's up here. What happens when you plug in a -1? -1 cubed is -1. That's right here. 0 is 0. So you can always plot points if you want to try to understand why these graphs take on these shapes. I did. But I asked you to memorize it. But to get a feel for it, maybe to help you memorize it, you sit there and you do this. Maybe it helps it sink into your soul a little bit. So one more. This guy is a little strange. You know, all these functions so far, I could ask you, what's the domain? What are you allowed to plug in for x? And you would say, anything, all real numbers. What are you allowed to plug in for x? Anything you want. What are you allowed to, ooh, this one's not quite. What's this guy's domain? If we're in the real number system, I know we went to imaginary numbers the other day, but if we're in the real number system, you're not allowed to have the square root of a negative number. So you're not allowed to plug in negative numbers if we're in the real number system. Look at my picture. Do you plug in any negative x's? Are negative x's in this domain? No. So the domain is x greater than or equal to 0. The picture shows that. The fact that there's a square root, that you can't plug in negative numbers. The domain is what you can plug in. Look at this one. What can you plug in here? All real numbers. What can you plug in here? All real numbers. What can you plug in for these x's? Anything you want. You're allowed to plug in negative numbers and positive numbers. The absolute value makes the answer positive. On this one, what are you allowed to plug in?
Positive numbers.
All kinds of numbers you're allowed to plug in. Who are you not allowed to plug in? Do you know the huge,
0.
what?
0.
0. In mathematics, about the most illegal thing, there's 2 kind of illegal things. You can't take the square root of a negative number in the real number system. In the real number system, you can't take the square root of a negative number. And the other big rule in mathematics, you can't divide by 0. You can't divide by 0. It's undefined. So his domain is all real numbers except 0. You can plug in all real numbers except 0. 0 is bad. X is not allowed to equal 0. Let me show you how that shows up on a graph. On a graph, that shows up as this vertical asymptote. I'm not really prepared to have a big discussion on asymptotes, but I want to tell you that there's a gap here. Because of the undefined place at x equals 0, there's a huge like ditch that you can't cross. And then if you plot points, this graph looks like this. And kind of, some student once told me it looks like a boomerang. Or actually it's a couple of boomerangs. I mean, it lives over here. Less than 0, there's a beautiful graph and curve here. Greater than 0, there's a beautiful graph and curve here. It's fine to be it's fine for x is less than 0. It's fine for x is greater than 0. But at 0, there's this darkness. You can't plug in 0. There's nothing there. There's no point there. And we draw this little dashed line just to indicate you can't plug anything in there. And that dashed line is called an asymptote. Asymptote, actually. Asymptote. And it's a vertical asymptote. Later we might do some horizontal asymptote. But that's the first time that's come up, right? We've done some cool stuff in this class. But today we just did a lot of cooler stuff. I mean, we just ventured into a big pile of functions here. I mean, you know, we spent a month on linear stuff. We spent a few days on quadratic stuff, and now all of a sudden, let's open our world up. We got some other functions we can memorize. Okay, that's good. Listen, I'm going to take a little 1-minute break. I'm going to come right back.